All right, second speaker is Anthony Unwin from Augsburg, if I'm not mistaken, and he will be talking to us about visualization of outliers, because we all have to deal with those occasionally if we get real data. So,
okay, good morning everyone. As the chairwoman said, my name's Anthony Unwin, and I want to talk about the black hole of outliers and hope that the O3 plot I'm going to suggest will shed some light on them. So what do we think about outliers? Well, if you're old enough like me, you remember Bob Beeman's jump in 1968, the long jump at the Mexico City Olympics, and that was an outlier. It was such an outlier that they had to measure it by hand because they weren't ready for such a long jump. It's still the Olympic record. It's still the second longest legal jump, and that is almost 50 years ago. Then, of course, if you're looking at outliers, you should certainly look at Barnett and Lewis and their third edition. I think it starts in the third edition, has this very interesting example of births in the United Kingdom and the difference between how lawyers look at these problems and how statisticians look at them. Always worth a read. But for something more modern, I don't know if you follow basketball, but the little figure, well, he's little. He's about 7 or 8 centimeters shorter than me. Isaiah Thomas is one of the star players of the Boston Celtics. The Boston Celtics have a roster of 16, 9 of whom are over 2 meters. So he is much, much shorter than most of his teammates, but he scores an awful lot of points, and he's a very good player. So he's also an outlier. So what are we thinking of outliers generally? Well, actually, it depends. They're different to the rest of the population. So if Isaiah Thomas was here today, he wouldn't actually be much different on height from the rest of us. But in basketball, he definitely looks rather different. But it's not just the population that matters. It's the dimensions you compare them on. I mean, maybe if we had Isaiah Thomas here and we compared him with the rest of us on the number of tattoos and the amount he earns and various other things, he would certainly be an outlier. But perhaps we talk a lot about outliers and populations, not so much on outliers and dimensions, which is something I want to come to, and obviously the outlier methods you use. Just a little bit about what we do with outliers. Well, it depends whether they're an exceptional case, like Bob Beeman's jump, possible fraud, errors of some kind, or just data from a different population. And then also what we really ought to get into is not single variable outliers, but multivariate ones. This is a parallel coordinate plot showing some outliers found by Lee Wilkinson's HD outliers algorithm, which is available in R, for the UCI adult data set, which has about 48,000 cases, and you can see the outliers found 3 4-dimensional outliers. But you can also see that 2 of them look like they're outliers on age and hours, and possibly if we just looked at the 2 dimensions together, we'd find those outliers on those dimensions alone. We wouldn't need 4. And the third outlier looks pretty outlying. It's not the most outlying, but pretty outlying on the variable weight. So maybe high-dimensional outliers are very often also low-dimensional outliers. So that's something to think about as well. What are we going to do about outliers? Well, points aren't outliers or not outliers. I think it's quite useful to think of them as potential outliers. So we're not saying it's a yes-no situation, and there are an awful lot of different approaches. What do we do with them? Well, we correct them, or we exclude them, or we maybe use robust methods. And we try and understand them. Well, we should try and understand them. And sometimes we do, to find out why they're different, and we look for additional information on them. With Bob Beeman, the fact that it was in Mexico City, there was a lot due to altitude. And as with all statistics, it's often a good idea to use graphics. Well, I would say that, wouldn't I? And here's the plot I want to suggest for a particular data set. So this looks a bit messy. I should say something about the data set. It's from the Bundestag election of 2005, and from the appropriate official website, you also get a lot of demographic variables for all of the 299 constituencies. And I took 4: car ownership per 1,000 population, the area of the constituency, live births per 1,000, and the population density. And what am I trying to show here? Well, here are the 4 variables, and each row shows a combination of the 4 variables. So the first row is just looking at population density on its own. The second row is area, and so on. You'll notice there's a little dotted blue line here and later here. So I'm separating the 1-dimension combinations from the 2-dimension, from the 3-dimension by these little dotted lines. And what I've got on the right is the number of outliers and which cases were found with that particular combination. So the first row is just population density, and there were 5 outliers found using the cutoff of 0.05 on HD outliers. And if you take the last row, that's a combination of car ownership, live births, population density, and only 1 outlier was found. So there's 2 chunks, and this just sort of lists it out. The reason I call it an O3 plot is it's supposed to be an overview of outliers, so OOO. There's a row for each combination of variables for which outliers were found, because those of you who were thinking, just a minute, there are more combinations of 4 variables than those rows he's got there. Well, any combinations where no outliers were found aren't included, just as there were a lot more points. There were 299 constituencies, but obviously I only plot columns for constituencies which were defined as an outlier for some combination or other. So we've got 2 sets of columns. We've got a blank column in between, sort of separated out. The grey cell entries on the left show which variables are in the combinations, red cell entries on the right, and so on. So, what can you see? If we take the constituency to the far right, that's Berlin-Kreuzberg, and you can see for several combinations, for 7 of them, it's found to be an outlier, and population density is always included. So that's possibly the driving force there. Although do note that we didn't find any outliers for the 4-dimensional picture, when obviously population density is there. What else can we see? Well, the second most often determined outlier, Kloppenberg-Wächter, it's mostly associated with the birth variable, not always the very bottom combination. That particular constituency was not defined as an outlier. Anything else? Well, we can take this one, Düren, and if you look closely at that, the 2 red marks in that column only occur for high-dimensional combinations. So actually, that's the only outlier which is not a 1-dimensional outlier of some kind. So it's kind of interesting. Car ownership doesn't seem to have any effect at 1-dimensional level, doesn't find any outliers, but you see there isn't a row with that single one, just as there is no row for all 4 variables together. And another interesting point, there are quite a large number of 2-dimensional outliers on the 2 variables area and population density, but if you look at the columns there, in each case, the 2-dimensional outlier is a 1-dimensional outlier on one of those 2 variables, so probably we're just picking up those 1-dimensional outliers in the 2-dimensional picture. So what am I claiming these plots show? Well, potential outliers, the variable combinations they're outlying on, variables common to those combinations, outliers with similar patterns of outlyingness, and we can also look at the variable combinations identifying outliers, finding the most outliers, finding similar outliers, and which low-dimensional combinations are critical. And if you've been thinking about this as well, I've obviously done quite a lot of sorting. I've sorted to get those sort of blue dotted lines. I've then sorted within that. I've also sorted the columns, all to make sure that I get some kind of reasonable picture. But there are, of course, problems of one kind or another. Methods of outliers, every method is described with great glee by their supporters, and they publish articles with very nice examples. But when you apply them to your examples, you then discover you quite often find far, far too many outliers. Doesn't matter what you're using. Sometimes you may also find too few, but that's a bit of an issue. The O3 plot is obviously not possible for more than a few variables. The German election data set I'm using has about 50 variables I could use. So if I would examine all those combinations, I'd only have to examine 2 to the 50 minus 1. And even if I didn't find many outliers for all those combinations, I think it might be a bit messy. So on the other hand, what would you do if you found a 50-dimensional outlier? I don't think we're even capable of working happily with 4 or 5-dimensional outliers, and I have this suspicion as well, and from the data that I see, that very often they're just low-dimensional outliers anyway. One thing one should say in a statistical conference, obviously I'm carrying out huge amounts of multiple testing. If you think about it, there's not just multiple testing really for one combination between all the combinations, and they're certainly not independent. But, you know, testing justifiably does not have the best of reputations, and it is useful to try and get guidelines and aid understanding, and that's what I'm trying to get at here, some understanding, not definitive yes or no. One other thing we could do is all of these outliers have been shown, have been outliers with this algorithm, HD outliers, at a 5% level. But maybe we could show different levels of outlyingness. So here's the same data set, and now I've got outlyingness at 1%, which I've colored red, and it's most dramatic. And there are not that many of those. 5% yellow, so obviously they're between 5 and 1%, and then I've added 10%. And the interesting thing is here, because of my sorting, the order of variables has changed a little bit, but this car ownership variable suddenly arises, and there's a whole string of new cases. Well, except for this one, which appears here and here, that's Duren. And it turns out that this is actually, they're not outliers at all, but they're an interesting group of Berlin constituencies who were all given the same car ownership figure because the constituencies were regarded as part of Berlin. And it turns out they're interesting in their own right, but they're not really relevant to outliers. So what have we been talking about? Well, I hope you've got the message that outliers are tricky, but you should have had that already. They're difficult to identify. It's difficult to understand sometimes. They may be an error or interesting or without influence. The choice of population to compare with is important, but so is the choice of variables. And this O3 plot is showing you all possible combinations of variables that might be interesting. So this overview of outliers O3 plot is a new tool for identifying and understanding outliers. With a slight postscriptum, I've chosen my data set carefully. Just like anybody else, I want to show something new. I choose my data set to show my new idea off to the best advantage. That's what we all do, that's what happens, and that's why when you test out a new method for yourself, you should always use your own data set, and preferably a real one because they have real problems. So let's see what happens if we choose a slightly different set of cases, and I'll take the first 5 variables in that data set and just choose those, and then I'll run the HD outliers on those. And so over half the data set are outliers. That just doesn't seem reasonable, does it? So there's some kind of problem there. So maybe, and that's all with one-dimensional combinations if you look at my picture. So maybe we could try fast PCS instead. So let's run that. And now things look a little more, but we're still finding huge numbers of outliers and all sorts of combinations. That doesn't look so great. So what about Bacon? Bacon has a reasonable reputation. Well, you know, now we're getting even more dramatic pictures. And funnily enough, the one-dimensional, we were finding too many one-dimensional with HD outliers. Now we're not finding so many. And just to finish off, since we're in Belgium, the DDC from Rousseau's group, and look at what happens there. And suddenly we don't find any high-dimensional outliers. So what is happening here? Well, it's basically that outliers are tricky. And what I've done in doing those analyses is not to show you that the O3 plot has weaknesses. I hope it shows you that it convinces you that the O3 plot has strengths, because it's illustrating the difficulties with using different methods and telling us we have to look more closely at comparing different methods, because that's really where the problems lie. And I hope the O3 plot will help you to shed light on these issues. Thanks.
Do we have any questions?
Have you considered turning the plot so the labels are easier to read?
I have no labels. I just have the X and so on. And obviously, it would make much more sense to put the constituency names on there. But let me show you why I don't. There is a constituency called Roth in Bavaria, which has 4 letters, so that would be fine. There's also a constituency in Brandenburg called Brandenburg an der Havel, Potsdam, Mittelmark 1, Havelland 3, Teltow, Fleming 1. We are talking about Germany after all. And if you can, I have looked for nice short names for the German constituencies so that I could attach them, but I haven't yet come across a suitable data set, and then exactly what you say, you could do that.
All right, thank you very much.